Section 7.2, the Bohr model of the hydrogen atom. The nucleus is incredibly small and takes up only a small part of the atom, but it is the majority of the mass because it's made up of the protons and neutrons. Now the electrons, on the other hand, occupy a large amount of space but add only a little bit of mass to the overall mass of the atom. Rutherford conducted the gold foil experiment and created the nuclear model, but then Mr. Bohr came along and he introduced the idea that electrons orbit the nucleus like planets orbit the sun. These orbits are quantized. Now what does quantized mean? It means there is no in-between. The piano is quantized. Only certain notes exist. For example, a C and a C sharp, you can't go in between those notes. Only a C and a C sharp exists. There's no note in between. It's not possible. Therefore, piano keys are quantized. This is a picture of the Bohr model of the hydrogen atom. So let's take a look. Here's the nucleus, and then each of these rings represents a fixed orbit that Bohr proposed. Now these orbits are quantized, meaning there's nothing in between. It's just a specific value for each orbit. So n equals 1 represents the first orbit, and that is always a certain distance from the nucleus. That distance is listed here. The second one is also a certain distance. Now you can't have an electron orbiting the nucleus at 1.5. That's impossible. It is quantized. It must be at 1 or at 2 or at 3, etc. This little red dot's going to represent our electron. So if we have an electron revolving around the nucleus at the closest orbit, that electron has a lower energy compared to an electron that is orbiting the nucleus at an orbit further away from the nucleus. So again, if an electron's close to the nucleus, it has a lower energy. If an electron is further away from the nucleus on a specific orbit, that has a higher energy. Now electrons can release energy or emit energy and fall down to a closer orbit. On the other hand, an electron can absorb energy and move to an orbit further away from the nucleus. On page 253 in your textbook, you'll see figure 7.10. Bohr's model was accepted because it explained the hydrogen line spectrum, which is right here. Now this line spectrum is specific to hydrogen. Every time the electron goes from n equals 6, this orbit, down to n equals 2, that orbit, it will emit visible light, and it will emit it at 410 nanometers. That's the wavelength. If you know the wavelength, you can find out the energy released. The light it emits always has the same amount of quantized energy, wavelength, and frequency. Let's illustrate this one more time. If I have an electron in an outer orbit, and that electron moves to a closer orbit to the nucleus, it will emit energy. Compared to an electron that begins at an orbit closer to the nucleus and moves out, that will absorb energy. That brings us to an equation where we can talk about the change in energy. The change of energy equals the final energy minus the initial energy. If that's the case, what is the change in energy for an electron going from an outer orbit to a closer orbit? The change in energy should be negative for an electron going from an outer orbit to a closer orbit to the nucleus. Let me illustrate that. If we start with a higher energy, let's give an arbitrary value of 4 joules. Okay, so I started on an outer orbit further away from the nucleus, and I ended, my final energy is much smaller because it's closer to the nucleus. We'll give that a value of 1. 1 minus 4 equals a negative 3. My change in energy is negative for an electron that is going from an orbit out here to an orbit closer to the nucleus. Energy, though, should be the absolute value. So the change of energy is negative for that example, but the energy should always be the absolute value. So the absolute value of -3 is 3. Now these are just example numbers. You'll be dealing with numbers that are much smaller. Here's an example problem. What is the photon energy of the light that produces the violet line in the hydrogen line spectrum? First, I need to take a look at what the wavelength is that I'm given. If you turn to page 253, you'll find the hydrogen line spectrum, and 410 nanometers is the wavelength for the violet line. So, can we convert wavelength to energy? Absolutely. What equation do we use? We use this equation. The energy of a photon is equivalent to Planck's constant times the speed of light divided by the wavelength. And we have the wavelength. This is a constant, this is a constant. If we do the math, we can find out the energy of that photon. Back to the problem. I've written down my equation right here. Let's first put in the information that I do know. I know Planck's constant. I also know the speed of light. And we have the wavelength. I like to change it into meters and then put it in the equation. So I'm going to do that problem just right here as a little mini separate problem. 410 nanometers. How many meters is that? Well, we need to do a little dimensional analysis. I know 10 to the 9th nanometers is in 1 meter. That would make my units cancel, giving me meters. I do the math on that and I get 4.1 times 10 to the -7th meters. I'm going to take that number and put it here. 4.1 times 10 to the -7th meters. This should equal the energy of that photon. I do the math on this problem, multiplying these and dividing by 4.1 times 10 to the -7th, and I get my energy, 4.848 times 10 to the -19th joules. What about significant figures? For significant figures, we need to keep it to 4.8 times 10 to the -19th joules.